Hello and welcome back. Today we'll be doing a question involving large matrices. These matrices should be larger than those seen at A level. Let's get started. A. Compute the determinant of each of the following matrices. Part 1. 1, 2, 3, 8, 9, 4, 7, 6, 5. Part 2. 1, 2, 3, 4, 3, 1, 4, 2, 2, 4, 1, 3, 4, 3, 2, 1. Part 3. 1, 1, 1, 1, 1, 1, 2, 2, 2, 2, 1, 2, 3, 3, 3, 1, 2, 3, 4, 4, 1, 2, 3, 4, 5. Part B. Invert matrix 1 both by cofactor expansion and by Gaussian elimination. Which method is more efficient? Part C. If matrix 2 or 3 is non-singular, invert it by the most efficient method. Pause the video to have a think, and once you're ready, restart to see if you were correct. Let's get started. Before we start on any of the parts, I will label these three matrices M3, M4 and M5 so that we can reference them easier later. Now let's begin with part A, part 1. Here we're using the rule of Saris, or Saris's rule, to calculate the determinant of M3, and this gives a determinant of negative 48, which is not 0, meaning that M3 is non-singular. Now we can calculate the determinant of M4. Using the old cofactor expansion here means that we need to calculate 4 separate determinants of 3 by 3s and then multiply them, giving a result of 0. Now we'll move on to part 3. Using the cofactor expansion means that we'll have to calculate 5 determinants of 4 by 4s, each of which is 4 determinants of 3 by 3. And therefore that means we have to calculate a grand total of 20 3 by 3 determinants, which is quite a bit of work. Instead, we're going to use some elimination to convert M5 into M5', which is an upper triangular matrix. Here, I'll be using row 5, take away 1 of row 4, and putting that back into row 5. Row 4, take away 1 of row 3, and putting that back into row 4, etc. And this gives that M5' is equal to the top triangular matrix filled with 1s, and the bottom triangular section filled with 0. From here, we can say that the determinant of M5 is equal to the determinant of M5', because we have not multiplied any rows by scalars and we have also not swapped any rows. Therefore, the determinant of M5 is equal to 1, which is not equal to 0. And therefore M5 is also non-singular. Now we can move on to part B. Here I've written out the cofactor matrix of M3. This is 21, negative 12, negative 15, 8, negative 16, 8, negative 19, 20, negative 7. Notice that I have hidden the calculation of 9 determinants here, and this would in reality be a decent amount of work. From here, we can say that the inverse of M3 is equal to 1 over negative 48 of 21, 8, negative 19, negative 12, negative 16, 20, negative 15, 8, negative 7. We can, however, also use Gaussian elimination to find the inverse of this matrix. We can take the old matrix M3 and the identity matrix I3 and combine them horizontally into one big matrix. Then we can perform row operations on the left-hand matrix to convert it to the identity matrix on the right, and we can perform the same row operations on the right-hand side, and once the left-hand side is converted to the identity, the right-hand side shall be equal to the inverse. Firstly, we'll take away 8 of row 1 from row 2, and we'll take away 7 of row 1 from row 3. Then we can take away 1 of row 3 from row 2. We'll then take away 8 of row 2 from row 3, and then we'll multiply rows 1 and 2 by negative 48. Then we can add 4 of row 3 back onto row 2. Finally, we can set the new row 1 to be equal to row 1, take away 2 row 2, take away 3 row 3, and this gives a right-hand side of 21, 8, negative 19, negative 12, negative 16, 20, negative 15, 8, negative 7, where the left-hand side is negative 48 of I3. This means that we can divide by 1 over negative 48 to give the exact same result as above. We can do the same with the 5 by 5 matrix. Here, I have skipped a few steps to give the upper triangular matrix we found in part A3, and I've done the same row operations to the right-hand side. Here, we can take away 1 of row 2 from row 1, then take away 1 of row 3 from row 2, etc., and this gives a right-hand side of 2, negative 1, 0, 0, 0, negative 1, 2, negative 1, 0, 0, 0, negative 1, 2, negative 1, 0, 0, 0, negative 1, 2, negative 1, and 0, 0, 0, negative 1, 1. This means that the inverse of M5 is, in fact, just the same as the right-hand side, since the determinant is 1. If you liked our video, please like and subscribe, and we'll see you next time for some more fun maths problems. Thanks for watching, and goodbye.